Hello everyone, and welcome back to our finite element analysis series. In part 1, we mastered the one-dimensional bar. We learned how to assemble a stiffness matrix and solve for displacement. But real structures are rarely one-dimensional. Bridges, cranes, roof trusses, these are all two-dimensional systems. Today, we are transitioning from 1D to 2D. We will cover rotation matrix theory, and we will implement a fully generic Python script that can solve any planar truss geometry. So, why does the analysis change when we move to 2D? In our previous lesson, the bars were aligned perfectly with the x-axis. We only had one displacement, u. But now, look at the diagram. In 2D, bars are oriented at an arbitrary angle, theta. This has three major consequences. First, an axial force in the bar now splits into components in both the x and y directions. Second, each node now has 2 degrees of freedom. We have u for horizontal translation and v for vertical translation. And third, because we have more degrees of freedom, our element matrix expands from a simple 2x2 grid to a 4x4 matrix. To solve this, we need to understand frames of reference. Think about a single bar. Its stiffness, K equals EA divided by L, is defined along its own axis. We call this the local frame. But to connect all these angled bars together, we must project this stiffness into the general system, the global frame. To do this projection, we use direction cosines. We define C as cosine theta. This is the change in x divided by the length L. And we define S as sine theta. This is the change in y divided by the length L. Now, let's look at the math. We relate the local displacements to the global displacements using a transformation matrix, which we call T. The formula for the global stiffness matrix, K_global, is derived by multiplying the transpose of T times the local stiffness times T. I won't make you do the matrix multiplication by hand, but you must memorize the result shown on the screen. The global stiffness matrix for a truss element is a 4x4 symmetric matrix. Let's look at the pattern in the first quadrant. Row 1 is C squared and C times S. Row 2 is C times S and S squared. This pattern repeats with negative signs in the other quadrants. This matrix is the heart of our Python code. Let's apply this theory to a concrete example. We have a triangular truss structure. Nodes 1 and 3 are fixed to the ground. Node 2 is the apex, and it is subjected to a downward load of 10 newtons. We have the material properties. Young's modulus, E, is 210 gigapascals. The area, A, is 2 times 10 to the power of -4 square meters. Our goal is to find exactly how much node 2 moves downwards. Let's open our Python environment. Step 1 is defining the geometry. Instead of hard-coding values, we use arrays. This makes our code generic. We define a nodes array. Row 0 represents node 1 at coordinates 0, 0. Row 1 represents node 2 at coordinates 2, 2. Row 2 represents node 3 at coordinates 4, 0. We also define an elements connectivity array. This tells Python which nodes are connected. For example, element 1 connects node 0 and node 1. Now, step 2, the calculation loop. We iterate through every bar in the structure. Inside the loop, we calculate the length L using the Pythagorean theorem. Then we calculate our direction cosines, C and S. Using these values, we build that 4x4 matrix we saw earlier. K_L equals stiffness factor times the matrix of C squared, CS, and so on. This creates the specific stiffness matrix for that angled bar. Step 3 is assembly. We need to place that small 4x4 matrix into the massive global system matrix. In 2D, the indexing is slightly more complex than in 1D. Because each node has two movements, node I corresponds to indices 2 times I and 2 times I plus 1. We use the command k_global square brackets indices plus equals k_el. This superimposes the stiffness of every bar into the main system. Step 4, System Resolution. We have the equation K times U equals F. First, we define the force vector F. We place a value of -10 at the vertical index of node 2. Next, boundary conditions. We know that nodes 1 and 3 are fixed, so we create a restraints array. 1 means fixed, 0 means free. We use NumPy slicing to extract only the free degrees of freedom. Finally, we solve it. U_free equals np.linalg.solve, open parentheses, k sliced, comma, f sliced, close parentheses. A calculation code is only complete if we can see the results. Here we plot the geometry. The black line represents the initial structure. The blue line represents the deformed structure. Notice how the triangle descends and compresses under the load. The supports at the bottom do not move, which confirms our boundary conditions were correct. To wrap up Part 2, we have successfully upgraded our code from 1D to 2D. The key takeaway is the rotation matrix. By projecting local stiffness into the global frame, we can analyze any geometry, whether it is a simple triangle or a complex suspension bridge. This script you see on the screen is fully generic. You can change the input coordinates, add more nodes, and the logic remains exactly the same. Thank you for your attention.